Alright guys, so this video is going to be fairly quick. We are going to be looking at comparing multiple equilibria. So this is going to deal with whenever we know an equation and we know the k expression, what happens if we change the equation in some way. So maybe we flip the equation, we might multiply the equation by a factor, or even add multiple equations together, similar to what we do in Hess's law. So if we reverse the way a reaction is written, so our reactants would move to the product side. That means that the variables on the equilibrium constant will flip from the top to the bottom, and that will end up doing the inverse of our equilibrium constant. So it will end up doing 1 over k if the reaction is flipped. So that will be something we will be looking at. We're going to do a couple examples using these in a moment. We also have to take into account if the equation we're looking at is a multiple of another equilibrium equation. So maybe the entire equation is multiplied by 2, or the entire equation is multiplied by 3. In those instances, the equilibrium constant is going to be raised to whatever that factor was. So if our reaction was multiplied by 2, whenever we're trying to find the new k value, that k value is now going to be squared. So whatever that multiplication factor is, we make that a power to find our new k value. And the last one we look at is if we have equilibrium reactions added together to get an overall reaction. Similar to what we do with H values in Hess's law. But what will be different here is the equilibrium constant of the overall reaction. So the equilibrium constant, the k of the overall reaction, it's going to be the product of all the individual equilibrium constants. So if our reaction would be 2 different reactions combined together, our new k value would be the k values for the individual reactions multiplied together. So whenever we did Hess's law with delta H, we added those. But whenever we're looking at k's, we're going to multiply those. So here is a way that these questions will come up. It says, is it a given temperature, K is equal to 1.3 times 10 to the negative second for this reaction. And it gives us the reaction of nitrogen plus 3 hydrogens, produces 2 ammonia. And it wants us to find the K values for the following. So you have to look and see what happened from the original equation to the one that we're looking at. So if we're looking at letter A, all of the substances are on the same side. Nitrogen is still a reactant, hydrogen is still a reactant, ammonia is still a product. But if you look at the coefficients have been divided by 2 or multiplied by 1/2 from the original equation. So whenever we're looking for K, we said whenever a reaction is multiplied by a factor, K is going to get raised to that factor. So to find our new K value, we're going to have to do K raised to the 1/2 power, since our reaction was multiplied by 1/2. So when we punch this in, sorry, I'm controlling both screens at the same time. So if we do 1.3 times 10 to the negative second raised to the 1/2 power, or to the 1/5, that should be the same thing as square rooting, we end up with 0.11, and there's no exponent there. We don't have to worry about scientific notation there. If we look at letter B, this reaction is flipped when compared to the original reaction. So we said when the reaction is flipped, you have to take the inverse of K. So we're going to have to do 1 over K, which is the 1.3 times 10 to the negative second. So whenever we put this in, we end up with, I'm going to leave it 2 sig figs, so it would end up being about 77 would be our new K value there whenever we're looking at the inverse. Looking at letter C, the ammonia is a product, so the reaction was flipped. So we're going to have to do 1 over K. But if you look, that is not all that has changed. The coefficients have also been multiplied by 1/2. So this is also going to be raised to the 1/2 power. So you can take that value we got from B, that was the inverse, and raise it to the 1/2 power. And leaving it at 2 sig figs, this is going to end up being 8.8. Alright, looking at our last one, we have everything is on the same side, so the reaction was not flipped, but all of our coefficients were doubled. So the reaction was multiplied by 2. So remember, anytime a reaction is multiplied, that means our K value is going to be raised to that power. So we're going to do the 1.3 times 10 to the negative second squared. Sorry guys, I hit the wrong button. So that is going to end up being 0.013, keeping it to 2 sig figs. And I don't have an example offhand of the one where you're combining. But say that this was the K for one reaction and the K for a second reaction is 3.2 times 10 to the negative third. And those two are being combined to get the overall reaction. Like we said, we would have to multiply those together. So we would have 1.3 times 10 to the negative second times 3.2 times 10 to the negative third. And our new K value, when we multiply those, this would end up being 4.2 times 10 to the negative fifth. So that's looking at comparing multiple equilibria. But like we said, pay attention to how did the original equation change to get the one that we're looking at. So you're either going to have to raise the K value to a power, take the inverse of the K value if the reaction flipped, or if you're combining equations, you're going to be multiplying those K values together.